All right, welcome back, everybody. We've almost made it through the week. I'm hoping I make it through this afternoon. All right, so we're going to actually break into content today, and we're going to be thinking first about the physics of how blood flows through. I'm not going to read the room. Who has taken physics before? Okay, cool. That is helpful reference for me. Yeah, I know our bio majors are required to take physics, but usually don't take it until after they have taken this course. So don't worry, we're gonna go from the beginning of what you need here, but we're gonna be starting with some kind of principles of how flow of fluids works in general, so that we can start to think about how do blood vessels work? What can change about blood vessels that makes your body work differently? So hopefully you reviewed a little bit of that material in chapter 14 since I saw you last. So I want you to chit chat to your neighbor for like 1 minute, thinking about what factors you think are going to be pushing blood through the vasculature, so our arteries and veins, and what you think could slow it down. So I should hear some whispering now. And then we'll go over it.
I think the size of small baby, small big are bigger. All right, circling back. I do have one organizational question for you guys first. That quick check question, I recommended that you check that you can do. When I wrote that down in the bullets of things you should look at, I was looking at an e-text. Is that also in the physical text? Does anybody have a text like that wasn't in? Okay, good. I just want to make sure that I'm referring to something that you all have access to rather than just one specific thing. Okay, so starting with that first part, does anybody want to let me know what factor you think is pushing blood through the vasculature? Yeah, did I hear pressure? Okay, so we're going to be thinking today about pressure and flow and the heart. Okay, so when we're thinking about the physics of our blood flow, the first thing that we want to think about is how this relates to pressure. Okay, so when we think about how our blood is moving through our circulatory system,
so through the heart and the blood vessels, we're going to be looking at different physical parameters that can vary. So this is going to come in next time when we pull in our different types of blood vessels. We're going to see that there are different physical properties that are going to vary between your, say, your arteries and your veins, or your arteries and your arterioles. So part of why we're trying to understand right now the way big physical principles influence blood flow is it so that later on, when we find out that some blood vessel is way narrower than another blood vessel, we'll be able to think about, okay, what does that mean in terms of what kind of blood is going to be able to travel through that part of the body at what speed. So that's kind of why we're doing what we're doing today. All right. So physical laws that we want to understand blood flow, blood pressure, and our circulatory system overall. We're going to be thinking about pressure gradients that we see. So we are going to have some equations throughout this section. So as we're going through, I'm just going to note that when we have a pressure gradient, you're going to see that noted as delta. This triangle is the delta. P, so P is for pressure. So when you see delta P, that's going to tell you that we're thinking about a pressure gradient or a pressure difference, okay? We're also going to be thinking about resistance. So resistance, you can think of as something that resists flow, right? So you can almost think of it like, it's not necessarily friction, but you can think about it like that, resistance, okay? When we say resistance, that's going to be a big R. Okay. And we're going to see that both of these factors are going to change our overall blood flows through our system. And really, these two factors would influence the flow of any fluid through any tube. So this is a physical property of the universe, not just of our bodies. So we're going to be relating changes in pressure, changes in resistance, and how that is going to influence what's going on in your body. Okay, so thinking about our pressure piece, I want everybody to just put your hand over your mouth and blow some air out. Okay, we gotta do that. Cool. All right, so when you're thinking about that, right, in this example, imagine that the air you are blowing is analogous to your blood, right? So air here is going to be your fluid in this imagination. We're going to see that these same principles that we talked about today, regulating blood, are going to come back and be relevant when we're thinking about airflow in and out of the lungs in our next unit as well. Okay. So when we're thinking about flow and pressure, what did you feel yourself doing in order to actually blow air? Where were you creating pressure? Or where did you feel any pressure in your body? You can do it again. You could do this all day. Do you feel any pressure when you do that?
Chest, stomach.
Yeah. So you're creating pressure using muscles in your chest, dividing your chest and your abdomen, right? You create pressure on the air here in your body. You create a high pressure environment inside. Now that we have high pressure inside our body, we now have a gradient, right? It's higher pressure inside, lower pressure outside. So air is moving from inside, high pressure, to outside, low pressure, right? So this works just the way our chemical gradients did when we were talking about electrochemical driving forces, right? When we think about pressure gradients, we are also thinking about things moving high pressure to low pressure, just like when you're thinking about things moving from regions of high concentration to low concentration. The same deal, just a new property that we're thinking about. So that's our pressure gradient, our pressure difference, was the difference in pressure of the air inside your body versus the relatively low pressure air in the room outside our body. Now, as we think about blood flow, we have to onto our understanding that our circulatory system is a closed system. Which means you're not like constantly losing blood, right? It's the same blood flowing around and around. Okay. So the blood flow is working just like liquid in a tube. That tube would have to be a ring going round and round and round. We're not losing any blood. So it's the same fluid. Okay. Other thing that we know now is that pressure is going to be important. Right? We want that blood to move. Needs to move through the tube, needs to circle around. So we're going to need to create a pressure difference in order to make that blood move. Okay. So that pressure is going to be the force exerted actually also by the blood itself. Okay. We're going to see blood flow happening from an area of high pressure to an area of low pressure. Okay. So this is kind of like when we were talking about the heart, right? So like our heart. Right, was creating pressure when it squeezed, right? And we traced what was happening to the pressure in the different chambers of the heart, right? That's coming back now, right? So that high pressure causes blood flushing to move from that area of high pressure to an area of lower pressure, okay? And we have factors that can change that flow or change that rate of flow, specifically resistance, which is going to be our big R, is going to be a factor that can lower our rate of flow. So an equation you are going to want to know is this one at the bottom. We're going to reshape it in all sorts of different types of ways, add on variables of like, where did we measure this pressure? Where did we measure that resistance, etc. I recommend not memorizing any of the reshaping versions, because if you can follow just this first equation, it should get you to like a lot of the observations and rules that we're going to have in the future. So we want to know this flow rule. So flow, and sometimes this will be referred to as bulk flow. You can think of it as our blood flow in this unit. All right, so flow is going to be equal to our difference in pressure, our pressure gradient. Right, so that's what's driving the movement is the blood, is that we have high pressure somewhere and lower pressure somewhere else, okay? Divided by our resistance, right? So our resistance is the force resisting that flow, right? So as we move forward, when we start to think about all kinds of changes that we're going to see happening in different blood vessels, in different organ systems, and so on, we're going to want to be able to relate these three concepts together, right? So, for example, when we think about, say, different hormones increasing the pressure, different parts of the nervous system increasing a pressure difference, right? We're going to notice that if we increase a difference in pressure, this is going to increase our flow, right? More difference in pressure, more flow. From this equation, we can also see, though, that if we increase the resistance, right? If we left this other stuff the same, right? Increase the resistance, we divide by a bigger number, right? So if we increase resistance, you see that we will decrease our flow, right? We'll go through all this stuff as it is relevant, right? But this is the kind of way we're going to hang on all these concepts we learn onto this bigger picture thing to make it a little easier for ourselves. So flow is equivalent to our difference in pressure divided by the resistance. So when we're thinking about these pressure gradients, right? Think about bulk flow, that just really means like the overall flow here, okay? We're going to have a pressure gradient in our cardiovascular system caused by the heart when it pumps out that blood. It's a big volume of blood into a relatively small space of the first heart into that aorta, right? So we're creating a pressure gradient for the bulk flow of blood. We have to have a gradient for circulation to continue, right? So we actually also have to have low pressure at the other end where we have blood coming back to the heart right? Because that's gonna be driving this overall flow through our whole big circuit, okay? Yeah, so on the right here, we can see some examples of flow, right? So we're putting some numbers here. So these are showing us some hydrostatic columns, aka water in glasses with a tube connecting them, right? So more water in this tube creates more pressure, right? So you can see this higher level of water is creating a pressure of 100 millimeters of mercury on this left side. We have less water over here on the right, so it's a little lower pressure, right? So you can think of it as being less heavy here. And so this is measured at 60 millimeters of mercury for a difference, a delta P of 40. Okay. If you're thinking about this, you're thinking about setting this up in your kitchen, saying you had the glassware, right? If you filled glasses like this, would hopefully not surprise you that they would even out, right? You'd end up with flow from that bigger column to the smaller column until they even out. That's the same thing that's happening in your body when we're thinking about these pressure gradients, right? It's all based on these same physical principles of this higher pressure causing flow towards the lower pressure, right? So in this top example, that's why we can see a flow of 20 milliliters per minute. We're not calculating these things for our purposes here. That's just a number for us. But once we've equaled out, right, once these two glasses of water are at the same level, we have no pressure difference, right? So if you imagine that flow rule, if flow is our difference in pressure divided by resistance, but our difference in pressure is 0, right? If you divide 0 by any number, doesn't matter what our resistance is, we're going to get a flow of 0. Right? So once they're equal, once there's no pressure difference, there's also no flow. A thing to note when we're looking at these diagrams, right? In C, you see something a little different than A, right? So you see a much higher column of water here on the left compared to what you saw in A. And same on the right, higher than what was on the right for A. So we can see that we now have a column at 200 millimeters of mercury versus 160 millimeters of mercury between those two. But this actually creates, what do you notice about these numbers? This delta P and that delta P. They're the same difference in pressure, right? Everybody see that? So it's the same difference in pressure, which is what we care about when we're calculating that flow, right? So it doesn't matter that the numbers in A and C overall, that 200 is greater than 100, 160 is greater than 60, right? What we care about is the difference in pressure, which is why we see the same flow for C as for A, right? So it's all about differences in pressure in this unit, right? Not overall pressure, differences in pressure is what's going to be important. These pressure gradients. Questions at this point about pressure gradients? So, reminder, haven't got the chapter 13 review up yet, but that will be coming soon. But I do want to make sure that we remember where our blood goes, right? So these are our chambers of the heart, right? So we're going to have right atrium, right ventricle, left atrium, left ventricle, and we've also got lungs on either side. Okay. And then we're going to go out to the body with our aorta. So I'll draw our body. Okay, our gingerbread person. I'm an amazing artist. Okay, cool. All right, so when we have blood flowing, blood starts at the heart in the right atrium. I can draw it so it's the heart, around the heart. Okay. So we're going to see blood coming into the right atrium. At the end of our last semester, we saw that we would go from the right atrium to the right ventricle. Okay. From the right ventricle, we go out through our pulmonary trunk and then our pulmonary arteries out to the lungs from the right ventricle. And then that blood needs to return from the lungs. It's picked up oxygen along the way, returns to our left atrium, okay, via the pulmonary veins. From the left atrium, we go to the left ventricle. And then we go out through the aorta to our systemic circuit. So out to the body, all through the whole body before returning to the right atrium. Okay. So we had our two circuits. We had our pulmonary circuit, right? So that part where we loop to the lungs, our pulmonary circuit. And then we had our systemic circuit from that left ventricle out through the body, returning via veins to the right atrium. This was our overall big picture of how our blood is flowing when we're thinking about the heart. Now we're going to be thinking about more of the details of what's going on there in those circuits that we're thinking about. And really, we are going to be focusing on that systemic circuit. So from the left ventricle to the aorta, through all the organs of your body, returning through the veins to the right atrium. That's really going to be our focus mainly in this portion of the course. Okay. So we do have pressure gradients across the systemic circuit and across the pulmonary circuit, right? So when we are thinking about, I shouldn't have erased it, when we're thinking about our heart and that blood flow. Okay. Drawing it the same. We got right atrium up here. That's going to be my right atrium. Here will be my left ventricle. Okay. Cool. I always draw that the same order. Okay. So when we're thinking about our pressure gradients, the places that we're going to be measuring pressure for that pressure difference that we're interested in when we're interested in flow, are going to be measuring our pressure in the aorta, right? As our mean arterial pressure, our MAP, right? So that'll be coming right out of that left ventricle, right? That's our big artery. Coming out of the left ventricle. It's got a big arch, okay? So that's where conceptually we're measuring MAP. Okay. Mean arterial pressure. And going through our systemic circuit, right? So we're going all the blood flow through the whole body, right? And we come back to the right atrium. Okay. Now, when we come back to the right atrium, we're coming back to the right atrium through two veins, both of which end in vena cava. You have one coming from the top part of the body, like from your head. You have a superior inferior vena cava, I will say, which you will eventually see in lab. Right, so there's a top and a bottom part, but we're just going to say vena cava for our purposes. So that's our big set of veins coming into the right atrium. Right. So that's our central venous pressure. So CVP. All right, so the A in MAP is for arteries, V in CVP is for veins. Okay. And those are going to be driving our overall flow of blood through our cardiovascular system, really. So we have that difference in pressure at the aorta versus the blood returning to the heart. So we're gonna see high pressure here in the aorta, right? And we're gonna see very, very low pressure here in the vena cava. E for our pressure. Okay. Those two things together are the relevant pressure difference for our cardiovascular system, right? So when I said we're going to be reshaping that flow equation, right? What I mean is that now we could write, right, our flow for the cardiovascular system is equivalent to MAP minus CVP divided by resistance, right? We now know that that is what delta P is. So that's just the same thing as writing what we wrote on the earlier slide, where we had that pressure difference divided by resistance, right? So depending on what we're focusing on, what we're trying to figure out about the body, we may be subbing different things in different parts of this equation. So that's that difference in pressure part. As we go through the different parts of the cardiovascular system, we're going to see that we do have differences in pressure across the board, really. So we're going to see that our arteries in the systemic circuit have very high pressure. Then we see a precipitous drop as we move through our arterioles and capillaries, right? And then our venules and veins, pressure of almost zero here in the systemic circuit by the time we get back to the heart. So it's that pressure difference that is driving blood flow. What is the case is the blood also has to get to the lungs to get oxygenated through that pulmonary circuit, right, where we had that right ventricle putting blood into that pulmonary trunk, sending it to the lungs, the pulmonary veins bringing it back to the left side of the heart. Right? The arteries involved in that pulmonary circuit do have a much lower pressure, right? So the pulmonary circuit does have a lower delta P, a lower difference in pressure, but we have a closed loop, so we can't really have the blood flow going to the lungs less and out to the body more, right? Because it's all got to go through the whole thing, the whole circulatory system. We don't want blood getting stuck in the lungs. Okay. So a thing to realize about those two circuits, right? So we can keep that flow the same through the pulmonary circuit and that systemic circuit, because we do have another factor that affects flow, which is our resistance. Right? So what I'm saying, right? Both of these circuits have to obey our flow, the equivalent to difference in pressure divided by resistance rule, right? We just saw that we had a much bigger pressure gradient in the systemic circuit, so like between the aorta and that vena cava returning to the right atrium, right? That difference was a lot bigger than it would be if you were to measure the blood in the pulmonary arteries going to the lungs versus the pulmonary veins returning to the left side of the heart, right? So if we didn't have resistance, the flow would be much greater, but we keep it the same because we can also change the resistance in order to change our rate of flow, our amount of flow. So the flow through these circuits is equal because when we have a lower pressure, right, if we divide that lower number by a lower resistance, we can get the same flow. So the pulmonary circuit, while it has less of a difference in pressure, it has a lower pressure gradient across the lungs, which is kind of nice for your lungs. It also has much less resistance, which is why we can have all that blood flowing nicely to the lungs at the same kind of rate as blood is flowing out to the rest of the body. We'll talk about resistance much more extensively when we get into talking about arterioles as well. So this is not like the only time we'll talk about how resistance affects flow. But we're going to go through a couple physical factors about resistance before we do that. So when we're thinking about that bottom part of the variable, or sorry, bottom part of the equation, right? So our flow, I'm gonna write this on like every slide. Flow equal to our difference in pressure divided by resistance, okay? So when we're thinking about how we could adjust our resistance, that big R, we have three factors we want to pay attention to. Okay. So you don't have to memorize this Cassell's equation. I cannot say that word. I don't speak French. So this equation at the bottom here, you don't have to memorize, but you do want to understand how these physical factors that we're listing for you would affect our overall resistance. Okay. So what we're looking at are things we can do to change resistance. So resistance is our big R. There is an equation for how you would calculate resistance. Okay. And that's here. This whole equation. You got a special box on it in your textbook. Right. So factors that we're interested in here. The most important for our blood flow in our bodies, right, is going to be, unfortunately, another R, right? And I'm going to rewrite this equation so it's in a way that's easier for me to see. Okay. I like things up and down. Okay. So the first thing on this list is our little r for our radius. Right? So resistance here is going to be affected by the radius here of our blood vessels. Okay? So we're going to be able to raise and lower our resistance by making our arteries, our arterioles, wider, so we can dilate them. We can increase that radius or increase their diameter, okay? Or we can decrease them. So looking at this equation, you don't have to memorize the equation, but we want to know what radius does, and we'll talk a lot about it. Okay, so thinking about this, I want you to predict for yourselves if I increase the radius, put up arrow here, so that little r gets bigger. We're making that blood vessel wider and wider and wider. We're dilating it. This would be vasodilation. What would this do to big R resistance? Is that number going to get bigger or smaller? Hearing some correct whispering. Okay, cool. So if our radius gets bigger, our blood vessel is wider, bigger hallway, okay? That means we're dividing by a larger number. So our resistance would go down. We have lower resistance to blood flow if we have a wider, more dilated, larger blood vessel. And that kind of, I do like to think about it like a hallway, which is why I said that, right? So if you think about a narrow hallway with lots of people going through, right? I feel resistance. You are resistant to go down that hallway, right? It gets nice and wide, right? Easier to go through, easier to flow through, lower resistance. So one of the big ways that we're going to be affecting resistance in our bodies is that we're going to be changing the radius first in this unit of our blood vessels. And then later when we're thinking about airflow and the lungs, we can change resistance by changing, right, like these same properties in the tubes related to breathing, right? So in our pulmonary system, we'll see the same sort of thing. So radius of the vessel is going to be super important for us in this class. There are other properties that can affect resistance, which will not in normal conditions be super important for physiology, because hopefully there are things that are not going to change dramatically, like in you or in your patients. But we do want to know that it could make a difference, just in case. These things can be weird sometimes. There are exceptions and things can go wrong. So the other things that can affect our resistance to flow are the length of the vessel. Okay. So, just an eraser. So if we think of our tube getting longer, right? So if length increases, what would we expect? Answering in your heads to happen to the resistance. Hopefully. We got a bigger number there. It's on the top now, right? So we get bigger resistance with greater length here, right? And then our final factor that we want to be able to think about is viscosity. Okay, and that's what this is. Our blood viscosity is a little more likely or more possible to change in a body than the length of your arteries would be. Blood viscosity is going to depend on like the number of red blood cells you have, and proteins in the blood. So it usually is constant, should be constant if everything's normal. But in certain conditions that affect the blood, you could see how that might change, right? So if we have a fluid that is more viscous, think of it as like more sticky, basically. So greater viscosity here. And do what to resistance? Yeah, great. Increase it. All right, perfect. Now we know everything there is to know about resistance. Questions about this concept of resistance?
So if we're asked on this, like in an exam, what would you given like the equation, and then we just have to know the relationships and the increase in the decrease in. Yeah, resistance.
For resistance, I'm not going to give you that equation. I won't ask you for that equation. So I would expect you to just know that relationship between radius and resistance, length and resistance, and viscosity and resistance. So know if one or the other goes up or down, what happens. Great. Lower rule at the top, I do recommend just memorizing. It's just 3 pieces and writing it down on a piece of paper the second you sit down with these. Okay. All right. So here is an example of that difference in resistance. Okay. All right, so for these 2 towers, these 2 glasses of water, we have a consistent difference in pressure. We know that it doesn't matter where we are, what matters is the difference in pressure. So it doesn't matter that the difference in A and that difference lower and down at B might be different, right? So our total amount of pressure at any point in this column doesn't really matter because we got the same difference in pressure. Okay. So here in A versus B, what we're looking at is a wider tube versus a narrower tube, right? Okay. So we can see here A with its greater radius, right? It's wider, right? And therefore, lower resistance has a greater flow rate than this narrower tube. So B with its lower radius and therefore higher resistance, despite that same difference in pressure, now has a lower flow rate. Now, hopefully this bit about tubes and resistance, while the word resistance may be new to you, like intuitively this idea of radius should be familiar from your daily lives, right? Like if you think about trying to drink something through a milkshake straw versus trying to suck something through a coffee straw, right? It's way harder. If you have to drink through a coffee straw, right, you have to exert more pressure, you have to pull with your muscles, with your body, it's exerting greater pressure in order to get a fluid to flow through a coffee straw versus through like a milkshake straw or a bubble tea straw or something, right? That's much easier. Even if your fluid is very viscous, because it's wider, because that radius is bigger. So now all it is that we know that this has to do with the fact that we change resistance by changing the radius of that tube. So I had low resistance up here for A, creating this faster flow. We have higher resistance here in B with that narrow tube, creating a slower flow. So when we talk about resistance and blood flow through your circulatory system, we're going to talk a lot about resistance when we're thinking about our arterioles specifically. So next week, we're going to be going through different orders of blood vessels, right? But we're going to have big arteries, then we're going to have smaller arterioles, then we're going to have exchange happening between the blood and the tissue at the capillaries and those networks of capillaries. Like we saw those capillary beds in the pituitary gland in NP1. Then from the capillaries, we're going to go into little venules, bigger veins, and then back to the heart. So that's the order of these blood vessels that we're going to be thinking about. So whenever you see this "ol" ending, right, I like to imagine that L is in there for little. So arteriole, little artery, venule, little vein. So resistance is going to come into play a lot when we think about our arterioles. Because the arterioles are really where we're going to see that we're able to regulate the size of that radius. They're small enough and have the right muscle and connection to our nervous system, the right receptors. It's going to let us really change how broad or how narrow those arterioles are. So when we talk about arterioles, we're going to be thinking about vasoconstriction. So constriction, think boa constrictor, right? Squeezing, squeezing, squeezing. You're making that radius smaller. Vaso is for blood vessel, right? So blood vessel constriction gives you a decreased radius, right? So we squeezed that arteriole narrower. So if we decrease that radius, we now know that that means we're going to see increased resistance. So greater resistance when we have that narrow tube due to vasoconstriction, which is a way that we could potentially slow down our flow, decrease that flow by putting a lot of resistance to the flow. And then we always have these sort of either or systems in our bodies. So we can go the opposite direction too. So same deal here, vasodilation. So think about like you go to the eye doctor and they dilate your pupil with those drops. The pupil gets real big, it dilates. Right, so vasodilation is increasing the radius, making it bigger, right? About our blood vessel specifically, vasodilation. Okay. So if we have a nice, great big radius, we've increased our radius. Okay. We now know, now that we've thought a little bit about resistance, if we have a nice big tube, this means we have less resistance to flow. So when you dilate something, you're going to be able to get more blood flow to that area. So decreased resistance, more flow, and this will be due to an increased radius, aka a bigger blood vessel. Pulmonary circuit features less resistance than the systemic circuit, has a lower pressure gradient required for blood flow overall. We are pretty much not going to talk about the pulmonary circuit kind of again until we get to the lungs. Okay, so when we're talking about this regulation, the radius and arterioles and all that stuff, we're really going to be focusing mainly on the systemic circuit. But this is the same kind of reason we can have lower resistance to the lungs, greater resistance when we're going out in the body, right? Is because we can change that resistance using our vessel radius, vessel length, and blood viscosity, although that would be the same between the lungs and the rest of the body. Now, when we're reshaping that big equation, one of the things that we might put in there, right? So we have our blood flow, okay? If we're talking about our systemic circuit, we know that that difference in pressure is actually coming from the difference in pressure in the aorta versus the veins. So our mean arterial pressure minus our central venous pressure was that delta P here. Okay. You're going to see that we also have a measurable thing in the body we might substitute in for resistance, which is going to be TPR for total peripheral resistance. Okay. What that is, it's basically that you can add up the resistance through all the different vessels, arterioles, et cetera, out in your body to get a grand total that you can look at when you're looking for flow through the whole system. Right? So total peripheral resistance is just adding together all the resistance in all the blood vessels involved in that circuit. So that's what TPR is here. Okay. So this is referring to our total network of blood vessels, because we're often interested not in blood flow, like just to your pinky finger. We're interested in what's going on with blood flow across the system. So that's why we created this idea of TPR, total peripheral resistance. Okay. So this way, we don't have to say that there's vasoconstriction specifically in your radial artery. We can just say that there's vasoconstriction in our network overall. All right. So if we have vasoconstriction in our network, I'm going to set there what that would mean, right? Vasoconstriction, constricting, making it smaller, smaller radius. Smaller radius means that we have greater resistance, right? It's harder to get through that narrow tube, greater resistance, right? So now, coming back to this equation, greater resistance goes here, right? Greater resistance in that network due to that vasoconstriction, right? Leads to decreased flow because we're now dividing by a bigger number, right? So that's how vasoconstriction affects the network overall. Basically, I'm just saying what works on the small scale also works on the big scale. Same deal with vasodilation. So vasodilation, dilating, is getting bigger. Bigger radius means less resistance. It's easier to get through the big tube, right? So that lowered resistance with vasodilation means we're dividing our pressure difference by a smaller number, which means overall our flow is greater. That's how these concepts are kind of going to come together and work together to get our overall flow, which we are going to end up relating to our heart stuff. Okay. We can actually start with this stuff next time as a review. So I will post for you what I want you to review for next time, but basically it's going to be the rest of section 14.1. So you read about pressure before today. I want you to go back and make sure that you understand the parts about resistance so that we can move forward and tack on thinking about specific blood vessels.